Hi, today we're going to talk about Bernoulli's principle. Bernoulli was a guy that lived back in the 1700s who made some observations about the way fluids moved through pipes and channels and things like that. He noticed that where there were restrictions in the pipes, rather than the water leaking out of the pipes, sometimes they would suck air in. And he wondered why that was. So he spent a good amount of time studying the phenomenon and came up with a formula. That formula is P for static pressure plus 1/2 rho V squared, which is dynamic pressure, equals a constant. What he meant by that was the total pressure has to be constant in order for his formula to work. Let's go through that formula one piece at a time. So the small letter p, the lowercase letter p, stands for static pressure. Static pressure is the pressure that is applied to the surfaces around the fluid when the fluid is still. This Greek letter rho, which looks a lot like a p, but it's kind of more round, represents air density. The v represents velocity, or the speed of the fluid, and we square that factor. And then we multiply all that by 1/2. That little piece is an important piece of the formula, not only for this purpose, but you're also going to find that shows up in lift. 1/2 rho v squared is the dynamic pressure. Dynamic pressure is what your airspeed indicator measures, and we'll talk more about that later. So, static pressure plus dynamic pressure is a constant. And this applies to any system where the total pressure is remaining constant as it moves through the system. One of the most common places to talk about Bernoulli is with respect to a Venturi. A Venturi is just a pipe with a restriction in it. As fluid flows through the Venturi, as it reaches the restriction, it speeds up and then slows it down again on the other side. Now, as you look at this for the first time, if you've never thought about this before, it may look like the fluid is being squeezed at the narrow part of the Venturi, but it's not. It's not moving fast enough to be squeezed. It simply speeds up and goes through that part of the Venturi faster, while the total pressure remains the same. So let's use some coins to build a little bit of an analogy here as to how the pressures change as we move through the Venturi. We're going to use the coins to represent pressure. In particular, we're going to have a stack for static pressure and a stack for dynamic pressure. The total pressure remains the same all the way through the Venturi. So, as the fluid goes into the Venturi at the beginning, it's going a certain speed, and we're going to represent that with the static and the dynamic pressure being about the same, so they each get the same number of coins. When the air gets to the middle of the Venturi, though, it speeds up. That means there's an increase in dynamic pressure. Since the total pressure has remained the same, those coins had to come from somewhere, and they came from the static pile. And so the static pressure pile of coins got smaller, representing a drop in static pressure in the middle of the Venturi. Once the fluid gets to the other end of the Venturi, they'll go back to being even again. This picture shows how we could measure static and total pressure. The static one is fairly intuitive. If we look up at the top, all we have to do is open up a little port that is not exposed to the direct flow. It's just measuring the flow, the pressure of the fluid perpendicular to its flow. The total pressure sensor goes out and ends in what some of you will recognize as a pitot tube. A pitot tube measures total pressure, and that's because when the fluid is brought into the tube, it's brought all the way to a halt. So it's measuring both dynamic and static pressure with that gauge. The total pressure equals the static pressure plus dynamic pressure. For us to measure dynamic pressure, we need a gauge that can measure the static pressure and the total pressure and subtract the static pressure from the total pressure. That is what an airspeed indicator does. The airspeed indicator is hooked up to both the static port on the airplane or helicopter and the pitot tube. There's a diaphragm that separates the two inside, and therefore it mechanically subtracts the static pressure from the total pressure to give you dynamic pressure. But rather than read it out into pressure, which would be kind of meaningless to you as a pilot, we label the gauge in knots or miles per hour. Here I have our Venturi with one of each type of gauge. We have, across the bottom, we have a total pressure gauge, and it is reading the same total pressure all the way through the Venturi. On the top side, we have a static pressure gauge, and then we also have the equivalent of an airspeed indicator, a dynamic pressure gauge. And it's measuring both total and static, and then subtracting the static from the total to give you dynamic. And we see that as we move towards the middle of the Venturi, the static pressure drops and the dynamic pressure increases. But the total remains the same. And then as we get to the far right end of the Venturi, the static and dynamic pressures go back to what they were, and once again the total is remaining the same. The Venturi works. You can measure this, and we apply it in various ways in the aircraft that we fly. The most common way is the aircraft that are equipped with float carburetors like 150s, 152s, 172s, R22s, R44s, most of them. Even the Piper Seminole has float carburetors in them, and they rely on a Venturi to create a low pressure area to draw fuel from a bowl into the carburetor throat. Another way that we have applied Venturis to flying is with a Venturi-driven gyro system. We don't use this anymore, but back in the 30s, 40s, and 50s, there were a lot of airplanes that were equipped with a Venturi bolted to the outside of the aircraft so that it was out there in the propeller and the slipstream. And it created a low pressure area that would suck air through the gyro instruments so that you could fly on instruments. Now there's an important distinction that you really need to get your mind around, and I don't think too many people really understand this as they teach people to fly. And that is that you can mess up Bernoulli's principle if you change the total pressure. So here we have a wind tunnel represented by the two horizontal lines, and we have an electric fan, which is at the moment turned off. So our dynamic pressure is zero, is indicating zero. Static pressure is straight up. Our total pressure is some amount that we're going to start with. Then we're going to turn the fan on. Watch what happens to both the dynamic and the total pressure here. Both of those went up. By turning the fan on, we added to the total pressure. And so the dynamic pressure was able to go up without increasing the static pressure. We're basically buying more dynamic pressure by pumping electricity into the fan and moving the air. If we go back to our coin metaphor and we start once again with the fan off, we have a total number of coins here that is all in the static pile. We have zero dynamic pressure. When we turn the fan on, we're adding pressure, adding coins to the dynamic pile, but we don't have to take them from the static pile because we've added them with the fan. And this is important because people get really confused about Bernoulli's principles in a lot of ways that we'll probably talk about in class. So the important takeaway here is the total pressure is constant in a Venturi, but static pressure does decrease in this restriction and dynamic pressure does increase in the restriction because of the increase in velocity. Well, what about the wing? We have the same sort of situation in the wing. The total pressure remains the same before, during, and after the wing is passing through the fluid. As the air passes over the top of the wing, there is an acceleration there. The air moving over the top of the wing is moving faster than the air on the bottom of the wing, and therefore we get an increase in dynamic pressure and a decrease in static pressure because the total pressure is the same. Bernoulli is very much involved with lift. The three incorrect theories of lift that I had you look at on NASA's website, 2 out of those 3 had Bernoulli involved. But that doesn't mean Bernoulli isn't involved in lift. It just was misapplied by those theories. In the case of the equal transit theory, the air molecules don't mate back up at the trailing edge of the wing, so that theory is incorrect. However, Bernoulli is in play as in creating lift. In the Venturi theory of lift, that is incorrect because there is no Venturi on the top of the wing. It does not form one side of a Venturi. But, once again, Bernoulli is in play here. You can measure the total lift being produced by the wing by measuring the difference in static pressure between the upper surface and the lower surface. That will give you the total lift. The total pressure remains the same as the air passes over the wing, and therefore the temperature and the density remain the same. All of this assuming that you're at subsonic speeds. However, none of this is due to a Venturi. There is no Venturi or even half a Venturi on top of the wing. Studying the changes in pressure around the wing is useful to us because it helps us understand why the wing stalls and why some wing shapes stall sooner than other wing shapes. However, Newton is very useful too, and we're going to cover that in a separate video.